Okay, so this is section 4.6. We're going to be talking about trigonometric identities. I'm actually used to calling this something slightly different. To me, trig identities is the things like the Pythagorean identities and the quotient identities, where tangent of theta you would equal sine of theta over cosine of theta. The reciprocal identities, for example, sine of theta equals 1 over cosecant of theta, or vice versa. To me, those are the identities. I'm actually more used to calling this trig proofs, or at least that's what they used to call it when I did this stuff. Um, One way or another, we're going to be using all of the identities, so the reciprocal, quotient, Pythagorean identities, and so on. We're going to use all of those in order to basically simplify trig expressions so that you can see that one thing equals another thing. Again, I'm used to calling them trig proofs, um, but hopefully you'll understand why that is as we go through it. So the first thing that we're going to do is basically just show how something might simplify. So if you have something like cotangent of theta and you divide that by cosecant of theta, well, that is not in its most simplified form. What we like to try and do to get something in a simplified form is to try and get rid of any kind of fractions and try not to, if possible, and it's not always possible, but try not to leave trig functions in the denominator. Um, in this case, because cotangent and cosecant both have a way to rewrite them in terms of sine or cosine, a lot of times that's going to be the easiest way to try and think about starting to simplify. So cotangent, we should know from the um, quotient identities, is cosine of theta divided by sine of theta. And then cosecant is 1 over sine of theta. And then we have fractions dividing fractions. So when you do that, you're going to multiply by the reciprocal of the bottom fraction. So ultimately what you get here is cosine of theta over sine theta times the reciprocal of the bottom, which is sine of theta over 1. And then the sine of thetas here are going to cancel out, which just leaves cosine of theta. So one thing that you should hopefully recognize, and I'm hoping this is an algebraic step that we kind of all already know how to do, but anytime your denominators are identical, and in this case the sine of theta here was the same as the sine of theta here, those are going to cancel out when you do the whole process of multiplying by the reciprocal. So that really is a kind of a shorter way to think of it, which just leaves you with cosine of theta over 1 or cosine of theta. So again, that's just the idea of reducing. So cotangent theta over cosecant of theta simply reduced to cosine of theta. Much, much simpler form. You could have one which is just as simple as cosecant of theta times the tangent of theta equals the secant of theta. And what you're trying to do is you're basically trying to show that these two things are identical. This is a very, very simple one to start with, but the idea is you want to take what looks to be the more complicated side. In this case, the left-hand side is definitely more complicated than the right, since the right side is just secant theta. And you want to rewrite it in such a way so that you can actually show that these things are equal. Well, once again, we're going to use the idea of changing these things into sines and cosines. This will not always be the easiest way, but in this case, I think it will be. So we can write cosecant of theta as 1 over sine theta, excuse me. And then tangent is going to be sine of theta over cosine of theta. And then on the left-hand side, the sine of thetas will cancel out, which leaves you with a 1 over cosine of theta equals secant theta. Oops, forgot to write my secant theta here. And then, of course, 1 over cosine of theta is secant theta. So basically, you've just verified that this is an identity because it's the same thing equal to itself. You can also use the concept of The odd and even functions, I'm not going to really go through that one as much, but it's not because it's not important. I just don't think we're going to have time to go through that one right now. So let's instead try something that's just a little more complicated looking. So this will actually be our first real example. The other two were examples, I guess, also, but so we'll do 1 plus tangent theta over 1 plus cotangent of theta equals tangent of theta. Now, the one thing that I will say is that there are several different ways you could go about trying to start solving for this stuff. And most of them could eventually get you there as long as you're doing correct mathematics. Some of them are going to ultimately make everything way more complicated than necessary. But there's basically a gazillion ways you could try to work this out. We're trying to find the most efficient way if possible. So what we might want to do here is think, well, okay, on the left-hand side, I've got 1 plus tangent theta over 1 plus cotangent theta. Ultimately, it's supposed to simplify down to just tangent theta. So again, we're going to work solely with the left-hand side because that is by far the more complicated looking side. So the idea is, yes, I could turn everything into sines and cosines, and yes, that will still work. But I also noticed that I'm trying to simplify to tangent theta on the right. So if I can put everything into terms of tangent, that might help. Well, I can write cotangent in terms of tangent because cotangent of theta is 1 over tangent of theta. So I'm going to keep the numerator just as it is, and I'm going to write the denominator as 1 plus 1 over tangent of theta. And I'm actually not going to write the right side out here, but it should be tangent theta all the way down. Okay, so that actually makes things look a little more complicated other than the fact that everything is in terms of tangent. So now what you want to do is you want to think, okay, now I've got this compound fraction. How do I get rid of the compound fraction? Well, what you want to do is you want to multiply everything by the denominator of the compound fraction part, which in this case is just a tangent theta. So I'm going to take and I'm going to multiply a tangent theta on the top and on the bottom. And when I do that, I'm actually not going to distribute the top just now because I think we'll have to undistribute it if we do. But if I were to write it out, that's what the numerator would look like. And then I am going to distribute the tangent theta through the bottom because that's going to get rid of the fraction. And ultimately what that gives me is a tangent theta here, and then 1 over tangent theta times tangent theta is just 1. And now hopefully what you can see, and this worked out really well, is on the top I've got a 1 plus tangent theta. On the bottom I've got a tangent theta plus 1, which is the same thing. So those are going to cancel out, leaving just tangent theta. And that, of course, is the right side of the equation. Now, you may not have thought to start it that way. You may have put everything in terms of sine and cosine. It's all going to still potentially work out. This stuff takes practice. It's definitely going to be something that you're going to have to look at and say, oh man, what do I have to try and start with? And a lot of times, believe me, when I did this, I started with things and I realized it was going way off the rails, so I started over. So it can get a little bit cumbersome, time consuming, and definitely frustrating if you pick the wrong method first. All right, so let's try sine of theta over 1 plus cosine of theta plus 1 plus cosine of theta over sine of theta equals 2 cosecant of theta. All right. There's no doubt in my mind the left side is way more complicated looking than the right side. We want it all on the left side to simplify down to 2 cosecant of theta. Well, we should know that in order to add fractions, you need to have a common denominator. So in this case, the common denominator is simply going to be multiplying the two denominators together. So my common denominator is going to be the quantity of 1 plus cosine theta all times sine of theta. Well, in order to get that, I'm going to have to multiply the left side of this thing, the left fraction, I guess you would say, by sine of theta over sine of theta. So I'll have a sine of theta here and a sine of theta there. Put a parentheses around these things because otherwise it won't look right. And to get the 1 plus cosine theta into the denominator, I'm going to have to multiply by another 1 plus cosine theta on top here, and a 1 plus cosine theta on the bottom there. All right, a little messy, but let's see what we get. So on the left-hand fraction, we're going to get a sine squared of theta. The denominator will be sine theta, 1 plus cosine theta. I'm not going to distribute it just yet. We may have to, but we'll see. Now on the top, I'm going to have to distribute that out. That's basically 1 plus cosine theta squared. So you can either FOIL it or whatever way works best for you, but that's going to be 1 plus 2 cosine theta plus cosine squared theta all over the denominator, the common denominator now. And all of that is eventually supposed to simplify to 2 cosecant theta. Now what I've done, there's absolutely nothing wrong with what I've done, so it's just going to be whether this simplifies the way we want it to or not. So now we can combine the numerators. So I'm going to get a sine squared theta plus 1 plus 2 cosine theta plus cosine squared theta all over my common denominator. And now let's see what we can do. Well, hopefully you recognize that I have up here a sine squared theta plus a cosine squared theta. And we should know that that simplifies to 1. So now I'm going to have a 1 plus 1 plus 2 cosine theta over the denominator. And 1 plus 1, of course, is 2. And I am writing this in way more steps than I normally would, but I want to make sure we know where this is coming from. Okay, it's getting a little bit simpler. You should hopefully see you can factor a 2 out of the numerator. And this is really good. And now we should see that that 1 plus cosine theta on the top and on the bottom are going to go away, which is going to leave us with 2 over sine theta. And of course, sine theta's reciprocal is cosecant, so this is 2 cosecant of theta. So that one did work out. And ultimately, that came down to knowing how to add the fractions by combining or getting a common denominator and doing it that way. Again, some of these are not short. Not exactly the easiest things to do. All right, let's do another example. I think the more examples that you see, the easier this stuff will ultimately be. I'm going to give you as much as I can for your toolbox here to be able to figure these things out. So let's say that we have tangent of theta plus cotangent of theta. That doesn't look like a plus, it's supposed to be a plus. There we go. Over secant of theta, oops, forgot to see, secant of theta, cosecant of theta. And believe it or not, all that is supposed to simplify to 1. Well, I've got tangent, cotangent, secant, and cosecant. I've got a whole bunch of stuff going on here. So my first thought is to definitely try to turn this stuff into sines and cosines and see what happens. So let's do that. So tangent is sine over cosine. So sine theta over cosine theta. Cotangent is cosine theta over sine theta. secant is 1 over cosine theta, and cosecant is 1 over sine theta. Well, the denominator can be written simply as one whole fraction because it's multiplication. So technically, I can just kind of extend that bar, multiplying the ones, just gives me 1 over cosine theta sine theta all in the denominator, which means I can bring that denominator up, flip it over, and multiply. So now we're going to get sine of theta over cosine of theta plus cosine of theta over sine of theta. That's still just the numerator. Now I'm going to bring that denominator up and flip it and multiply. So I'm going to multiply each term by cosine theta sine theta. Okay, distributing this to this first term over here, the cosines are going to cancel out because I'll have one on the top and one on the bottom, and that's going to leave us with sine squared of theta. And then when I distribute this one into here, the sines are going to cancel out because I'll have one on the top and the bottom, and that'll leave us with a cosine squared of theta, which of course is 1. So believe it or not, that did simplify very nicely to 1. All right, let's do one more example. And of course, this is not going to be every single possible thing you could do, but I'm going to give you as many, like I said, little things as I can here. There's so many other ways that you could go about doing proofs or verifying identities. So let's say that we have 1 minus sine of theta over cosine of theta equals cosine of theta over 1 plus sine of theta. So technically, in this case, neither one of these things looks any less complicated than the other on one side or the other. Typically, if you have a single term in the denominator, that is going to be considered more simple than something where you have a quantity in the denominator. So, for example, here we have cosine of theta only on the left-hand side of the equation. That's going to be more simple than the right side of the equation where you have 1 plus sine of theta. So let's try and work with the right side of the equation here. So in order to do this, I'm going to introduce something that I don't think that we've talked about very often, but what we're going to do is we are going to multiply by what is called the conjugate of the denominator. And the conjugate is basically the same terms, but with a different sign in the middle. So the example here would be, I'm going to multiply the top and the bottom of this by 1 minus sine of theta. 1 minus sine of theta. And again, I think we've talked about it a little bit, but not a lot. The purpose of doing this is that when you distribute that in the denominator, when you multiply by the conjugate, ultimately the inside terms are going to drop out. So you're just going to end up with being the first times the first and the last times the last. Let's see if this helps us out at all. I mean, like I said, I'm not even sure if I picked the right way. I think I did, but we'll find out. So in the numerator, I'm not going to distribute just yet. We may have to, we'll see. But the denominator, 1 times 1 is 1. Again, if you were to do the outside and the inside part of this foiling it, you would get a negative sine theta and a positive sine of theta, which would cancel out. That's the purpose of this. And then you'll have minus sine squared of theta. Okay, and the nice thing about that is that 1 minus sine squared of theta comes from the Pythagorean identity, which is just cosine squared of theta. So we have cosine theta, 1 minus sine of theta over cosine squared of theta. And this actually looks like this is going to work very nicely because one of those cosines on the denominator is going to get rid of the cosine on top. So on top is cosine. That's going to get rid of that one, that's squared there. So ultimately, we are left with 1 minus sine theta over cosine theta, and that is exactly what we had on the left-hand side. Technically, we could have done this the other way, I believe. You could have multiplied by the conjugate of the numerator on the left-hand side, and it would have worked out pretty much the exact same way. All right, so this is the idea about verifying identities. You really need to know your properties. You need to know your identities, your reciprocals, what goes with what, and it's honestly going to be a lot of trial and error. It's not a bad idea to think about turning everything into terms of sine and cosine first. Um, and if that doesn't work, then go with something else. Use some of your other identities. Again, we had 3 Pythagorean identities. The most important one is the sine squared plus cosine squared equals 1. We had the quotient identities, which is tangent and cotangent being a form of sine or cosine, and then all the reciprocal identities. Those are probably the most important ones. And just to remind everybody, I probably should have done this in the beginning. I believe that came from section, I'm actually drawing a blank now. I believe it came from section like 3 point something. Let me think. Yeah, I think it was section 3.2. So you can go back to section 3.2 that we did. And I'm pretty sure that's where we introduced all the identities. If it's not that one, it's something very close. All right, that should be plenty enough for this particular video. Our next section, we're going to end up introducing some formulas, just the sum and difference formulas that you're going to need for trigonometric functions.